Hello, welcome back to AE 2220 Dynamics. In this video, we're going to continue our discussion of rectilinear motion, focusing on how to determine the motion of a particle. So motion is most often determined by knowing the acceleration of a particle, and there are several different cases that occur. We're going to go through one case here. There are other cases that we're not going to cover, but I'm still going to have to label this as case 1. So in this case, the acceleration is going to be given as a function of time. So a of t is equal to, well, just some function of time. And then we can recall that the acceleration a of t is equal to dv dt. And in this case, we're dropping the vector notation because we're dealing with a rectilinear motion, which is in a single direction. So there's no need to have that vector notation. And so then we can rewrite this as dv is equal to a of t times dt. From there, we can integrate both sides, and we'll find that the integral of dv is equal to the integral of f of t dt, such that v of t is equal to the integral of f of t dt plus a constant. And this constant here, this is arbitrary. It's just an arbitrary constant at this point, meaning it could be anything we want, which also means that the motion is not unique. It can be, we have an infinite possible motions. So to define the motion uniquely, we must specify some initial conditions. That is, what is the position at time 0 and what is the velocity at time 0. So let's let, at this point, x of 0 equal to x sub 0 and v of 0 equal to, we'll just say v sub 0. And then we can integrate from v0 to v, and we're going to use a special v here as a dummy variable, and I'll talk about what a dummy variable is in a moment. And then we're going to integrate from 0 to t of f of tau d tau. And again, the special v that I drew here, this is a dummy variable, as is this tau. And we'll write out what a dummy variable is, just to be careful. So I'm going to say dummy variable here. And actually, let's not write it there. We're gonna come here, and we're gonna say this behaves exactly as t, but looks different to avoid confusion. Same thing with this special v. It behaves exactly the same as the velocity, it just looks different. So that we can integrate from v0 to v and 0 to t. And then solving, what we'll get now is v of t minus v0 is equal to the integral from 0 to t f of tau d tau, or that v of t is equal to the integral from 0 to t f of t d tau. I'm sorry, that should be f of tau actually, f of tau d tau plus v0. So now we've gone ahead and define the motion uniquely. We no longer have an arbitrary constant. We now have this known initial velocity. All right, so then to find the position, we're going to integrate the velocities. So if we recall that v is equal to dx over dt, then dx is going to equal to v dt, and we're going to do the same kind of integration we did before. So we're going to have an integration from x0 to x, and we're going to use the Greek letter c, or c, but a lot of people call it c, so we'll just go with c because you're more likely to hear that than c. So Greek letter c is equal to the integral 0 to t of v of tau d tau equal to the integral of 0 to t of the integral from 0 to tau of f of big T d big T, and this is still time. We're now using a second dummy variable, big T, plus v0 d tau dt. Sorry, just d tau. So from there, what we end up finding then is that the position x of t is equal to the integral from 0 to t times the integral of 0 to tau f of big T d big T d tau plus v0 t plus x0, and that is now our position. Let me go ahead and move that little rectangle. And that's our position now as a function of time. So sometimes we're given that the acceleration is a function of the position, or the acceleration is a function of the velocity. And then you can go forth and just derive the velocity or the position based on this. And these are where these extra cases come in. We are not going to cover those in this class, but they do exist.